two last points about the determinant. One is comparing the determinant of a matrix to the determinant of a constant times a matrix. So it's kind of tempting to think, well, shouldn't you just be able to move the constant outside the determinant? And the answer is no. No, you cannot just do that. And the reason is, think about how these two matrices are different. These two matrices, well, think about how they're different by comparing their rows. Each row has been, to get a C times A, each row of A has been multiplied by C. Well, we know that if you multiply a single row by a constant, the determinant gets multiplied by that constant. But how many rows, right, in C times A, how many rows have been multiplied by C? Well, all of the rows. How many rows is that? Well, if A is n by n, then there are n rows. So n rows have been multiplied by C. So the determinant of C times A, it's the same as the determinant of A, except we have to multiply by C once for every row that's been multiplied by C. But there are n of them, so we have to multiply by C n times, so that means it's C to the n. Okay, not just C, but C to the n. So just as a quick example, let's compare the determinant of, I don't know, 2, 3, 4, minus 1, and the determinant of, let's say, 4, 6, 8, minus 2. Right, now this second matrix is just twice the first one, so what we ought to get for this second determinant is, well, let's calculate the first determinant. So minus 2, minus 12, that's minus 14. So this second matrix is twice the first one, so its determinant ought to be 2 to the second, because there are 2 rows, times the determinant of the first one. So 4 times 14, that's 4 times negative 14, that's negative 56, I guess. So we ought to get negative 56. Just to check, we get, so negative 8 minus 6 times 8. So negative 6 times 8, that's negative 48 minus another 8, that's minus 56. So, you know, it worked. It worked. The other thing I wanted to point out about the determinant is how column operations affect the determinant. So we haven't talked too much about column operations. There are the same column operations as there are row operations, right? You can interchange two columns, you can multiply a column by a constant, or you can add a multiple of one column to another. And the thing is, figuring out how all of those change the determinant is pretty straightforward, because column operations for, or applied to a matrix, are the same thing as row operations applied to the transpose, right? So any column operation on a matrix is just a row operation on the transpose of that matrix. And we know that a matrix has the same determinant as its transpose. So to figure out what a column operation does to a determinant, we can think about the corresponding row operation applied to the transpose, because the determinants will agree. But we know what row operations do to the determinant. So, right, interchanging two rows makes switches the sign of the determinant. That's what we figured out. But that means that interchanging two columns does exactly the same thing. It also changes the sign of the determinant. Right? We know that multiplying a row by a constant multiplies the determinant by that constant. And so the column operation does the same thing. If you multiply a column by a constant, that also just multiplies the determinant by that constant. And then, of course, adding a multiple of a row to another row does not change the determinant. And so adding a multiple of a column to another column also does not change the determinant. So, the short version of all of this is column operations do exactly the same thing to determinants as row operations do.